Hello everybody. We are going to talk about the last part of this chapter that we will cover. There are other parts that we will not cover in this series. We will end up with the mass transfer correlations for packed and fluidized beds. And again, I told you before in the previous videos that this chapter is only showing some examples, and these examples are very little compared to all the information that are available in literature. So whoever is interested can search for more relations that are more suitable for his or her case. What we are interested in here is just to show some examples and know how to deal with these kind of equations in different systems. So before we go through the equations, I would like to take some time to talk about the packed bed and fluidized beds. What is the meaning of them, and how do we or why do we use these kind of beds? So for the packed bed is it's a hollow tube or a hollow pipe or column, and fill it with a packing material. This packing material can take many shapes, and this is one example, which is the pull rings, if I recall it correctly. And as you see, we have here a gas liquid contact process. We have a liquid flowing from up to down, and the gas going from down to up. And as you see here, the packing material is just an inert material. In this case, it's just an inert material that provides area of mass transfer. If the column is hollow, then the liquid will fall and the gas will go up without enough time to contact each other. So we provide this contact area and the contact time using this packing material. And as you would expect, the packing material has one or more functions. It can be an inert packing, like in this case, if you have a gas liquid operation like distillation, absorption, like stripping. For all these operations, you have a packing material that acts as only an area of mass transfer. So it only provides area big enough for mass transfer. So if we can get it as big as possible, it's going to be better, of course. It's an inert packing, meaning that it does not contribute to the process taking place here. So it does not matter what is the liquid, what is the gas. It's inert for both of them. It's just a surface. It can be part of a mass transfer process in cases like adsorption or desorption. For these cases, you have a solid particle that either takes something from the gas phase or liquid phase, or releases something to the gas or liquid phase. So in this case, it's a part of the mass transfer process. The last case, which is a very, very famous case, which is the catalyst. So it's part of the process. It increases the rate of reaction, so it makes the reaction faster. And of course, as we talked about this before in I think chapter 22, in the very first chapter in this series, when we were discussing the pore diffusion, and we said that the active sites or the active parts of the catalyst are inside the pores, so there is mass transfer process included in this catalyst function as well. So it can take any one of these depending on the process that we are dealing with. So for all of them, we prefer to have a packing material that has high surface area per unit volume, which we call the specific surface area, and to have high porosity. And the porosity means that there is big void fraction or space inside the particles, so that we don't have a lot of pressure drop or resistance to flow for the two phases. So the equations that we use we'll deal with are used for beds of spherical particles. So here we assume that the particles are perfect spheres, and we have relations for liquids in beds and relations for gases in beds. And of course, the gas or the liquid is the phase where mass transfer is taking place in. So the relations would be function of Reynolds number. We have here the epsilon, which is the porosity. The porosity is a value that is between 0 and 1. So it's a fraction of the total volume. So it has to be from 0 to 1. We have this relation, which is epsilon multiplied by JD. We mentioned JD before, and I will talk about it in more details in few minutes. But this is the relation. If you can get JD, you can get mass transfer coefficient out of it. So this is epsilon, the void fraction, this is Reynolds number, and this is valid for a Schmidt number from 165 and 70,000 and 600 and for epsilon from 0.35 to 0.75. The same for the other relation. It's very similar with the difference of these two values, the number and the power, and it's valid for Reynolds number from 55 to 1500 and for Schmidt number from 165 to 10,690. This is the relation that we use for gas. It's the same shape of the relation, and it's valid for Reynolds number from 90 to 400. Now let's talk more about JD. So JD is a parameter that we mentioned before, I think in the beginning of this chapter, and we said that it's Sherwood number divided by Reynolds divided by Schmidt power 1 over 3. And if you expand Schmidt number as KL over D and Reynolds number as VL over nu, we will talk about U average shortly, and if we do some simplifications, L will cancel out with the L and rearrange the equation. We will end up with KC over U average multiplied by Schmidt power 2 over 3. So if we calculate JD from this relation, we can calculate KC from this relation. So KC is JD multiplied by average velocity divided by Schmidt power 2 over 3. So this is how we calculate JD. Reynolds number is calculated, of course the density is the density of the fluid phase, either it's liquid or gas. dP is the particle diameter of one or one sphere of the particles. Mu is the viscosity, of course, and then U average is the average velocity of the empty bed. So actually, if you're thinking of this, the velocity that we calculate should be the flow rate divided by the actual area of the flow. The actual area of the flow is less than the total area of the vessel. If this is a cylindrical vessel, then the area is pi over 4 d squared, which is the d is the diameter of the vessel. But this area is not it's not all this area is available for flow, because a big part of it is occupied by the solid particles. So we should account for or consider the area of the space or the empty spaces in this column, and this is going to be very difficult to calculate, and it's not uniform. It's different from here to there to there to there. So each point is different, especially for spherical particles that are randomly distributed. So you cannot calculate an actual area of the flow. So to make it easy and simple for us, we do our calculations using the average velocity or superficial velocity of the empty bed. So assuming that the bed is empty, we assume that the area of flow is the total area of the column, which is pi over 4 d squared, and then we do our calculations based on this. And this is not the actual velocity, I know, but this is the velocity that's used to predict these equations. So these equations are based on the average velocity, average superficial gas velocity of the empty bed. So this is how the equations are. Of course, this will make the calculations much simpler, and these constants here that we see are all predicted based on the superficial gas velocity. The other type of the beds, which is called the fluidized beds. If you have a solid or a bed of solid particles and you have a gas that is flowing from bottom to top or from down to up, the particles will stay in their place and the gas will flow between the particles. And if you increase the velocity, the same behavior will continue until a specific velocity which is strong enough or high enough to drag the particles. So in this case, the particles would be fluidized. It's like they are not stationary in their place, they are flowing in the air, just flowing in the air. And this video is a very nice video. You have here a bed of solid particles that are put in layers with different colors, and these colors are very, very nice, because you will see how the colors will change due to the fluidization. So we have a gas that is flowing from the bottom, and as the gas flows, it's exceeding the fluidization velocity, and the particles start to move due to the motion or the velocity of the gas, and this will make some turbulence and mixing between the particles. So they are not anymore in layers, they are uniform color. If the velocity of the gas is below the fluidization velocity, the particles will stay in their place, the gas will go between the pores and get from the other side. So this velocity that is high enough to, or at which the particles will start to fluidize, is called the minimum fluidization velocity. We use the minimum or the fluidization or the fluidized beds because they have a lot of advantages despite being hard to control. You can imagine how hard to control a system like this, and especially if you have hard particles, they will collide with each other. You have to make them from materials that are strong enough to prevent any abrasion or any fracture due to the knocking or due to the collision between the particles and between the particles and the walls of the vessel. And that's why it's kind of tricky, and of course you have to control the velocity very well, because if the velocity is lower than the minimum fluidization velocity, the particles will settle down. If it's higher than the designed velocity, it might drag the particles up outside the vessel. So this has to be well controlled, but we can take the risk of doing all this because there are many advantages of this. The main advantage is that the surface area that we achieve using the fluidized bed is much larger than the surface area for the packed bed. For packed bed, you have particles that are sitting on each other, so there is some area of the particle that is dead. What is here and here is not usable area. The particles cannot go in between the particles and go in this area. So when you fluidize the particles, you get them away from each other and you expose the whole area of the particle to mass transfer or the reaction process, whatever the case that you are dealing with, and of course this will increase the rate of mass transfer or the rate of reaction. One other advantage is that we are dealing with high velocity, and this high velocity will increase the turbulence and consequently will increase Reynolds number, consequently will increase the mass transfer coefficient, so it increases the rate of mass transfer. So there are many advantages of using the fluidized bed. The correlation that we have is used for both gas and liquid phases, or fluidized beds by gas and liquid. And as you see, it's the same. Epsilon JD equals this. It's functional Reynolds number. JD is the same as before, or what we did in the packed bed. So this is the last correlation. Next video, inshallah, will be the last one. We will solve one more problem to kind of get practice or some practice on the equations that we mentioned here, and this will be the end of the course. So I'll see you next time, inshallah. Goodbye.